Hello and good day to you watching this video. So in this video, we would now be discussing about the horizontal distribution of seismic shear per floor. Okay, so in the previous video, we have already solved for the story shear. So this was our example before. And when we say story shear, that is basically the shear that is acting upon a certain story. Okay, so it is as simple as that. And suppose that this is already the building that you're analyzing, and this is to be the vertical distribution of base shear or of the seismic shear, again, per floor. So if we want to know, let's say the story shear that is acting upon a certain floor, what we would be doing is that, of course, we would just be analyzing that particular floor by cutting, let's say, the building upon that point. And again, by story shear, as per defined before, that is the accumulated forces from that particular floor up until the top floor. So basically, guys, let's say that this is the vertical distribution of the story shear on top of the build or on top of the story that you are analyzing. What you would be doing is that you will be adding all of them. So upon adding all of them, it could now be represented by one force. Okay. So this force here, once again, is what we would be calling the story shear, which is once again equal to all of these forces. Okay. So now that you know the story shear, as structural engineers, what we want to do next is that we must know the forces or the shear that will be carried by each of the lateral force resisting members, or in other words, the columns or maybe the shear walls. So say that in this figure here, this is the plan view of that particular floor. And as you can see that there are plenty of columns there. So how much of these columns are carrying the story shear? Okay? So, or maybe it's the other way around. Say that how much of the story shear is being carried by each of these individual columns. Okay? So, let me just show this code provision here. So, for the horizontal distribution of shear, so it is said here that for the design story shear, it is actually the sum of the forces Ft and Fx above that story. So that was what I was saying a while ago. It shall be distributed to the various elements of the vertical lateral force resisting system in proportion to their rigidities. Okay, so in order for us to know how much of the story shear will be acting upon the individual lateral force resisting elements here, such as the columns, the next thing that we should know is the position of the story shear itself. So in plan view or in side view, as you can see here, we already know that the story shear is acting upon this floor. But what about if you would be looking at the building in plan view? So this is now the plan view. So where is the story shear located? Okay, so is it here? Is it here? Is it here? And the like. Okay, so from that, guys, we would now be discussing about these key terms in order for us to better understand the principles of the horizontal distribution of seismic shear. So in this slide, as you can see that we have plenty of key terms that we should be accustomed to, such as center of mass, center of rigidity, stiffness, eccentricity, and etc. Okay, so first things first, what is the center of mass? Basically, when we say center of mass, so let me just type the definition here. When we say center of mass, this is basically the average, call this the average, ano ba yan? Ba't ayaw? So basically, when we say center of mass, so let me just type the definition here. So again, when we say center of mass, this is basically the average position of the floor mass. Okay, so what is floor mass? Basically, this consists of floor loads, maybe wall loads, or basically the seismic dead load on that particular story. Okay? So, again, it is the average position of the floor mass. When we say floor mass, it is the seismic dead load. So, in the previous video, we already know that seismic dead load consists of dead load, as you know, and in some cases, 25% of live loads in a situation wherein let's say that you are designing a building, whereas it has warehouses, storages, and the like, and etc. So once again, it is the seismic dead load on that particular story. So if you can remember from your lecture before, from your lower years in, let's say, statics of rigid bodies, or even in strength of materials or mechanics of deformable bodies. So suppose that we would be having a certain beam. So in this particular beam, it is now subject to a horizontal a uniform distributed load. So suppose that that is a perfectly uniformly distributed load. If you would be solving for its resultant, it is actually located at the midspan. Okay. So again, that is just for a review. So from that, guys, once again, if you would be getting the resultant of it, it is located at the midspan. So this position here is basically the center of mass already. So in a situation we're in, let's say that we would be having a certain beam, and say that the beam would now be carrying a triangular load. If you would be getting its resultant, it is actually located here. Whereas if you would be measuring from this distance, this is 2/3 the length. And if you would be measuring from this distance, it is 1/3 the length. Okay? So that is basically the center of mass of each of these beams. However, since we are now to analyze a whole floor, it is now in terms of a 3D space. So, well, basically, if you have a wall load here, a wall load here, let's say a floor load here, and let's say a different floor load here, if you would be getting the average position of all, or in other words, the location of the resultants, that is basically the center of mass. Okay, so what is the importance of center of mass in our lecture? So its importance is that for the center of mass, this is also the location of the story shear. Okay, so if this is now the location of the story shear, we could now safely assume that, for example, you have solved for the center of mass to be located at this point. And if that is now the location of the center of mass, meaning that the story shear is acting upon that particular floor, regardless of the direction. So supposedly, or suppose that the earthquake that you are analyzing is going towards this direction, meaning that the story shear would be acting upon this particular point, which is, again, the center of mass. Okay? So next up, we would now be discussing about the center of rigidity. And when we say center of rigidity, this is also known as, so aka center of stiffness. Okay? So when we say center of rigidity, that is basically the center of stiffness. And as for the stiffness itself, we would be discussing that first before going back to center of rigidity. So when you say stiffness, I think you are already familiar with this term already from your previous subjects. So I think you have already heard of the axial stiffness. So when you say axial stiffness, this is basically AEL over L. And when we say flexural stiffness, you also have the formula EI over L, and etc. But in our context for this video, we are to be discussing about the lateral stiffness. Okay, so when you say lateral stiffness, this is the numerical representation of how hard it is to displace a particular floor on the lateral direction. So suppose, guys, that let's say that we would be having a particular building here, and let's say that we would be applying lateral loads, for example, a story shear. The tendency of this building is that it would now sway along this direction. And as you can see, guys, that this here has displaced. Okay? So, in order for us to take into account how hard it is to displace, we are now to solve for the lateral stiffness. Okay? So, these are the different formulas that we could use for the lateral stiffness. So, take note that these are only for columns. And as for shear walls, as you know that shear wall is basically a very oversized column. So ang shear wall po malaking column lang po 'yan. So in some cases, the formula for the lateral stiffness for shear walls and that of the column would be different. especially if the shear wall is very big, in such a way that its lateral displacement is being not contradicted, but rather its lateral displacement is being countered, I should say, by the shear force of a shear wall. And from that, we could not use these formulas any longer. So once again, in this video, we are only limited to this lateral stiffness formulas. This is only for columns, okay? And if you would be analyzing the units here, you would actually be um, what you call this, you would be resulting to a unit of Newton per meter, or let's say kilonewton per meter, or maybe Newton per millimeters. So from that, guys, when we say lateral stiffness, this is basically the force required for it to displace. Okay, so this is force per unit displacement. So in this unit here, Newton per meter. So suppose that the lateral stiffness K, by the way, the variable here is K. Suppose that K is equal to 100 or 1000 kilonewtons per millimeter. If this is the lateral stiffness of a particular column, it should take 1000 kilonewtons in order for that particular column to displace by 1 mm. So if this is the column, and if we would now be applying 1000 kilonewtons upon it, it would only displace by 1 mm. Okay? So that is the meaning of lateral stiffness. So for our series of lectures, we would be using this particular formula, which is fixed at both ends, because we are assuming, or we will be assuming, that our building will be a special moment frame. And when we say moment frame, suppose that this is the building and we have beams per floor. If we would be analyzing a particular column here, so suppose that this is the column. And of course, in that particular column, we have a beam here. And we also have beams here. So for special moment frame, we are to consider that these are fixed supports. So we have moment restraints here. And from that, apologies. So from that, we could now say that it is fixed at both ends. So for SMF, this is the most common lateral stiffness that you will be using. Okay. So going back to the center of rigidity, if you already know the stiffness per member or per a column, you could now solve for the center of rigidity. So again, this is the center of stiffness, or this is actually the point in a particular floor, which is, well, basically the strongest point, since it is the centroid of all of the stiffness of all of the columns. So if you can remember from your previous subjects, once again, the Variance theorem. So under the Variance theorem, we could say that in order for you to solve for the centroid, you would be getting the product of the total area, 80, times the location of the centroid, bar x, that is equal to a1 times x1 plus a2 times x2 plus a3 times x3, and so on and so forth. Okay, but take note, guys, that for this variance theorem, this is in relation or in reference with the area. But for center of rigidity, this should be in relation with the stiffness. So from that, we would be changing this formula in such a way that all of the values for letter A, or the area, will be changed by the stiffness. So from that, this is now equal to stiffness, or the total stiffness, times bar x. This is now equal to the stiffness of the first column multiplied by its position, and so on and so forth. Okay? So from that, guys, you could now solve for the to call this, for the location of the center of rigidity using this modified variance theorem. Okay? But take note here, guys. Let me just emphasize here. So let me just clear this up and rewrite our formula here. So again, kt times bar x is equal to k1 x1 plus k2 x2 plus k3 x3, and so on and so forth. And like what I have said earlier, that the value of K that we will be using is 12 EI over H cube or L cube. Okay? So with that, in that case, guys, you would just be substituting this equation to this equation. However, guys, in a situation we're in, let's say that all of these columns have the same property. So for example, all of them are steel. So if all of them are steel, the value for the modulus of elasticity is equal to 200,000 megapascal each. Okay? So that is basically a constant. And suppose that you are analyzing a particular floor, whereas all of the columns would be having the same height. So again, all of them would be having the same height. Then we could now say that in this particular equation here, the value of h is also constant. Okay? So constant. But again, this is not always the case. There are some cases wherein one column is longer than that of the other. For example, for high ceilings, like that. So again, the that might vary. But in a situation we're in that the value of h would be constant, then as you know that the values of E, 12, and H would be constant. And if we are to make use of that equation, so for the value for KT, when we say KT, that is basically the summation of K or the summation of 12 EI over H cube. So again, this is equal to 12 EI1 over H cube times x1 plus 12 EI2 over H cube times x2 and so on and so forth. And if we would be solving for the bar x, so by the way, there should be a bar x here. So if you would be solving for the bar x, so let me just write at this part. So bar x is now equal to, so 12 EI1 x1 over H cube plus 12 EI2 x2 over H cube all over the summation of 12 EI over H cube. Take note that if once again all of these members would be having the same material, which is steel, and let's say that all of them would be having the same height, again, the values for E and H would be constant. So from that, guys, this would now cancel out, except for the value of I, of course. So in that case, guys, we could also simplify the equation. Erase ko lang po ito. So let me just simplify the equation that we could also make use of this equation. So the total moment of inertia times bar x is equal to I1 x1 plus I2 x2 plus I3 x3 and etc. Okay? So again, guys, you can only make use of this equation if all of the members would be having the same material and height. Okay? So again, you could only make use of that equation of if all of the materials, or sorry, all of the columns would be having the same height and same material. But of course, let's say that in your building, it is rather composite, whereas some columns would be concrete, some columns would be steel, and in some shear walls, of course, it would be concrete. So in that case, guys, we would now be making use of this formula. Okay, so next up, aside from those, we must also know what eccentricity means. So suppose, guys, that let's say the center of mass in this building was solved to be located here. Let's suppose that that is the center of mass. Okay, so also suppose that you have solved for the center of rigidity and it is now located at this particular point. Okay, so as you can see that the center of mass and the center of rigidity did not coincide. And from that, guys, suppose that, let's say that we would be having a certain story shear, or let's say that we are analyzing earthquake along the horizontal direction. So suppose that this is now the story shear. Again, the story shear would be located at the center of mass. Okay. So in that case, as you know that the center of rigidity is basically the strongest point on a certain floor, if you would be taking into consideration all of the stiffness. So meaning that that is the stiffest point in the floor. And from that, guys, if this is the strongest point or the stiffest point in a particular floor, there is actually a tendency that the building would twist. Okay? Why? Why is that the case? Because we now have an eccentricity. And when we say eccentricity, that is basically the perpendicular distance between the story shear and the center of rigidity. Once again, this is now E. Okay? So again, this is now the perpendicular distance between the story shear and center of rigidity. And take note that the story shear is actually located at the center of mass. Okay? So take note, guys, it must be perpendicular with the shear force. Okay? So meaning, if let's say the earthquake or the load is acting towards this direction, if it is acting towards this direction, then meaning that this is now the value of eccentricity. Okay? So, let me just erase this first. So, analyze lang po muna natin itong story shear na to. So, again, let us name that story shear as V. Okay. So, if there is an eccentricity, as you know that for the presence of eccentricity, it would now be introducing a moment. And from that, guys, if this is, let's say, the point or the rigid point, and let's say that this is now your lever arm, and this is the force, the tendency of this building is that it might twist. It will twist, I should say, about this direction. So this torque here or this torsion here is equal to force times lever arm. Okay, so again, this is the force and this is the lever arm. And if, in that case, if that is now the force and the lever arm, this torsion here is now what we would be calling the natural torsion. Okay, so once again, natural torsion is, of course, the product of shear force and eccentricity E. Okay, so again, the formula here, so for the natural torsion, that is equal to force times eccentricity. Okay, so this is as simple as that, and as you can see that it would now cause the building to twist, and from that you should also take that into consideration in your designs. Okay, so next up, we now have this term which we call accidental torsion, and for starters, guys, or let me just show this code provisions right here, which I would not read any longer. Rather, explain ko na lang po kung ano pong ibig sabihin nun. So, when we say accidental torsion, what is the difference between accidental torsion and natural torsion? So, again, for for our natural torsion, that is basically equal to shear times eccentricity. But what about for accidental torsion? So, for natural torsion, the eccentricity came about by the distance between, let's say that once again, this is the center of mass. And let's say that this is the center of rigidity. If let's say that this is now the direction of earthquake, so meaning that this is now the story shear, this is now the eccentricity. Okay, and once again from natural torsion, for this particular moment, torsion is equal to force V times eccentricity. But how sure are we that in real life the location of center of mass is really located here, or let's say that the location of the center of rigidity is really located here? So there might be some inconsistencies between your design and that of the actual construction. So for example, you want to design a certain column to be 400 to 400. So that was your design. But in real life, maybe in the construction proper itself, instead of them creating, let's say, this column, which is 400 by 400, what if during concrete pouring, its actual size would be, let's say, 402 by 402. So from that, if you would now be having a different dimension of column, the stiffness would also vary, and thus it might affect the location of the center of rigidity. Or for example, for the center of mass, suppose that in your design, you are designing or you have designed a certain floor to carry floor tiles with, let's say, weight of 1.1 kilopascal. But maybe in real life or in actual scenario, they have bought or you have bought a tile which weighs, let's say, 1.2 kilonewton per square meter. So from that, of course, the center of mass will also change. So any variance in center of mass and center of rigidity would also affect the eccentricity, of course. Okay? So in order for us to take into account that uncertainty, we would now be making use of the code provision for accidental torsion. So what the code provision suggests is that for the eccentricity, so let's say that this is the effective eccentricity that we will be using. Okay? So this is equal to the eccentricity, the original eccentricity, plus 5% of the perpendicular dimension of the building to the story shear. Okay? So in this example here, guys, so suppose that this is, um, let's say B, dimension B, and let's say that this is now dimension L. Since the story shear would be acting upon this direction and the perpendicular distance of the building that is in relation with this force is B. So from that, we would now be getting 5% of B. Okay? So from that, for example, B is equal to 100 meters, and let's say that the eccentricity is, let's say, 1 meter. Okay, so for the effective eccentricity to take into account accidental torsion, this is equal to 1 meter, 1 meter, I should say, plus 5% of 100. So 5% of 100, which is a very big building, by the way. So from that, guys, we will now be making use of 6 meters of eccentricity. By the way, I'm not sure if this is really realistic, but this is just an example. Okay, so next up, for the last definition that we should take into consideration in order for us to better understand the principles of horizontal distribution of seismic shear is the term diaphragm. Okay, so suppose that once again, this is the building or this is the columns. And for example, that we do not have any beams or columns. Oh, sorry, no. As you can see, we have columns here. Suppose that we do not have any beams, we do not have any bracings, we do not have any slabs. So again, they are individual columns. So suppose that we are to apply a lateral force here. So the only thing or the only column that would withstand that is just this particular column. It is just it. Okay? So what about, for example, if we are to have, once again, this is that particular force. But suppose that we would be connecting this columns right here with a beam. And from that, guys, if they are now connected with a beam, and let's say that we are to subject it with the lateral force here, all of these individual columns would now have their share. Okay, so hindi lang po isa, lahat na po sila. And from that, guys, what if, for example, we would be adding beams here? So, suppose that we will be having beams to all of these members. And let's say we would also be adding slabs, again, for all of the members. Meaning, if all of the slabs will be applied to all of these members and all of the columns will be connected with beams, meaning that the force will be transferred to all of them. Okay? So that is basically the action of a diaphragm. Okay? So when we say diaphragm here, these are members which transfer lateral loads to other lateral force resisting elements or members. Okay, so again, LFRM stands for lateral force resisting members. In some cases, lateral force resisting elements, and in some cases, lateral force resisting what do you call this, um members. Okay, so again, this consists of columns, shear walls, etc., etc. Okay, so again, for the diaphragm, these are not diaphragms, rather the diaphragms are the members which transfers the lateral loads. So this includes the following but are not limited to. So we have beams, we also have slabs. Okay, so in order for a certain column to help this particular column, they must be connected in a way. Okay, so we must need to add diaphragms upon it. Okay, so with that, guys, we would now be having our first example problem. So here.